Hi, I'm Alan Hawes. Welcome back to Amazon FreeRTOS 101 with the Cypress 43907 and 54907 Wi-Fi development kits. In this video, I'm going to talk about the application folder structure and how to debug AFR examples in Wicked Studio. Project files for Wicked Studio are available in the Amazon FreeRTOS folder that you downloaded from Git. Here's the path. These files are mapped to the root folder inside of the Wicked Studio IDE Project Explorer window. There are multiple demos that we include with the AWS code. By default, the MQTT demo is enabled, but you can change to the demo whichever one you like from the list. To select a demo, first go to the Project Explorer and head to Config, Files, AWS Demo Config. Change the #define for config MQTT demo enabled to any demo that you want to try. Only one demo can be enabled at a time, but no one will stop you if you want to combine two demos into one. I have to say that I'm not, what you would say, always the best at following the rules. In fact, the other day my wife was yelling at me, imagine that, "Alan, why is it that you think the rules only apply to other people?" Anyway, do whatever you want to. I always do. The file demos/include/IoT demo runner maps the demo entry function to the corresponding function for the demo that you selected. In this case, the demo function is run MQTT demo. We will look at that function a bit later in this video. The complete Wicked Studio SDK is available under the Amazon-FreeRTOS vendors/Cypress folder. The SDK is linked into the Project Explorer under AWS Demos, Vendors, Cypress, Wicked SDK. Note that even if you use the latest Wicked Studio IDE, Amazon FreeRTOS will still use the SDK from the Amazon FreeRTOS path so that everything works together properly. Now, let's look at the example code to see how it's structured. Application code main.c contains main, which is, get this, the main entry point for the application. Main performs the hardware initialization that should be done prior to starting FreeRTOS. It creates a logging task and then starts the FreeRTOS scheduler. After the scheduler is started, the application startup hook is invoked from the RTOS tick timer callback the first time it's called. The application daemon task startup contains hardware initialization, including initializing the Wi-Fi, generating a random seed, and doing the AWS certificate and private key provisioning, and then it starts the demo task. I said in the last video, and I'll say it again here, security matters, and we've made it so that you don't have any excuse not to have good security in your IoT devices. Note that the pointer to the function that corresponds to the demo that you selected in the AWS demo config.h file is passed as an argument to the task creation. In this case, it's mapped to run MQTT demo. The same structure also passes in the network type, which is Wi-Fi in this case, and it passes callbacks for connection and disconnection. The run demo task first initializes and checks for the right interface. In our case, that interface is Wi-Fi. More specifically, it's my kick butt 43907 Wi-Fi. Look, it's easy to make Wi-Fi work on your desk or in your lab, but to make Wi-Fi work well in the real world, that's a whole different story. The fastest way to get a boatload of bad product reviews on Amazon is by deploying flaky Wi-Fi. Just don't do it. Friends don't let friends use flaky Wi-Fi. Now back to the code. Next is an informational message that's logged into the console. When you ran the demo, you would have seen something like this. Network type 1 here means Wi-Fi. Once that's out of the way, control is passed to the appropriate demo function that was originally passed into the task as a pointer. Remember, in this case, it is the function run MQTT demo, which is in IoT demo mqtt.c. Most of the action for this demo is accomplished in the run MQTT demo. After defining some variables, the MQTT library is initialized and an MQTT connection is established. Then it subscribes to MQTT messages using the prefix of IoT demo followed by /topic 1, 2, 3, 4. Once that's completed, the project publishes all of the messages. A semaphore is used so that the firmware waits until all of the publishes have been completed before it continues on. Once all of them are received, it removes subscriptions and closes the connection, does a little bit of other cleanup, and then it exits. Now that we have some idea of how a project is architected, let's dive deeply into the setup of debugging. I'm going to use Wicked Studio 6.2.1, but you can use Wicked Studio 6.4 or later versions as well. Start by choosing Run Debug Configurations. Under GDB Hardware Debugging, click on the 43XX Wi-Fi debug windows. Now right-click and pick Duplicate. Change the name in the top of the window to AFR Debug or any other name you prefer. In the Main tab, click Browse under Project and select AWS Demos. Next, under C++ Application, click Search Project, select Last Build ELF, and click OK. Before launching the debugger, we need to make one more change. Currently, RTOS thread resolved during debug is not supported for AFR in Wicked Studio. As a workaround, go to the Wicked Studio installation folder to open the file shown here in a file editor and go to the line that has target name configure RTOS auto RTOS wipe. Remove the RTOS auto from that line and save the file. Now click Apply and then Debug. If you've connected the board and everything goes well, the debugger will start up and it will pause execution in the start.gcc.s file. You can open IoT demo mqtt.c and put a breakpoint at the line that says if acknowledgement length is less than 0 inside of the subscription callback function by double-clicking to the left of the line or by right-clicking and selecting Toggle Breakpoint. This function is called by the MQTT library each time a message is received for a topic that you have subscribed to. It should be noted that if you wait indefinitely on a breakpoint inside of a thread with a network connection in it, you have a much larger chance of getting disconnected. Kind of turns out that timing in Wi-Fi networks actually matters, and halting the processor for a long time probably isn't going to work well. So stopping execution while they're inside of an active connection should be used sparingly. Press the Resume button. It will take several seconds to connect to your Wi-Fi access point and then establish an MQTT connection with AWS. Once that's done, subscriptions are made and then finally you start to publish messages. Whenever a message from one of your subscription triggers the callback function, execution will stop at your breakpoint. Keep hitting Resume and notice that it stops at the breakpoint each time a message is received from the message broker. This takes us to the end of this set of tutorial videos. I hope you enjoyed them and that you learned a lot about how to use Amazon FreeRTOS with the Cypress 43907 and 54907. I think I've given you the pieces parts you need to build your own awesome IoT connected Amazon FreeRTOS devices. We plan to make some more videos to cover advanced topics and new Cypress devices as they come out. So check back again and you'll see what's new, including soon a set of CYWxx907 devices. You can post your comments and questions in our developer community, or as always, you're welcome to email me a personal comment or question to alan_hawes@cypress.com or tweet me at AskIoTExpert. Thank you.